Good morning. In the previous classes, we had discussed about methods such as bisection method, method of false position, which belong to the class of enclosure methods, which help us to determine a solution of an equation of the form f of x is equal to 0. Now, we would like to develop numerical methods which belong to the second class, namely fixed point iteration methods. We will define what is a fixed point for a function and relate the solution of this fixed point for a function to that of solution of an equation of the form f of x is equal to 0, and develop a numerical method which belongs therefore to the class of fixed point iteration methods. So, let us try to understand what we mean by a fixed point for a given function. So, a point P is a fixed point for a given function g if g of p is equal to p. If this condition is satisfied by some p, then we say that it is a fixed point for this given function g. Let us consider an example. Say g of x is x square minus 2 in the interval minus 2 less than or equal to x less than or equal to 3. So, I am interested in determining the fixed points of this function. By definition, I should be able to find out a p such that g of p must be equal to p, or in other words, this p must satisfy the equation p square minus 2 equal to p. So, p square minus p minus 2 must be 0, and so this is p minus 2 into p plus 1 equal to 0, which gives p equal to 2 and p equal to minus 1 are points which have the property that g of p equal to p. Let us just check what happens at p equal to minus 1. G at minus 1 is minus 1 the whole square minus 2. So, it is minus 1. And what about g at 2? That is going to be 2 square minus 2, which is again 2. The question now arises, given a function g, does it always have a fixed point, or are there conditions which should be satisfied by g so that the fixed points for that function in an interval are guaranteed? So, let us now consider the following result, which gives us the sufficient condition for So, we now give the sufficient conditions for the existence and uniqueness of a fixed point, and it is given by the following result. it says if G is such that G belongs to C of a b, namely it is a continuous function on the closed interval a b, and G takes values in that interval. So, G of x belongs to a b, then G has a fixed point in that interval a b. So, the conditions that G must satisfy are that G is a continuous function on the closed interval a b and G takes values on the interval a b. And if these conditions are satisfied, then G has a fixed point in that interval a b. So, if in addition G dashed of x exists in the open interval a b and that a positive constant k less than 1 exists with modulus of G dashed of x less than or equal to k for every x in this open interval a b, then the fixed point in that interval a b is unique. So, consider the function g of x given by x square minus 1 by 3 on the interval minus 1 to 1. Let us try to determine the fixed points of this function which belong to the interval minus 1 to 1. We observe that G is continuous on this closed interval minus 1 to 1. Let us find G dashed of x, and that is 2x by 3, and it is 0 when x is equal to 0. And what about G double dashed of x? That is 2 by 3 and it is positive. Therefore, G has a minimum at x is equal to 0. An extreme value theorem implies that the absolute minimum occurs at x is equal to 0 for the function g, and the value is g of 0, which is minus 1 by 3. Also, the absolute maximum occurs at x is equal to plus or minus 1, and the value at those points plus or minus 1 are given by 0. So, g has minimum value minus 1 by 3 and its maximum is 0. So, g takes values in the interval minus 1 to 1. G is a continuous function on the interval minus 1 to 1, and therefore, by the first part of the theorem that we have shown, G has a fixed point in the interval minus 1 to 1. Now, let us also see what happens to G dashed of x. G dashed of x is 2x by 3, and the absolute value of G dashed of x is less than or equal to 2 by 3 for every x in the interval minus 1 to 1. So, there exists a k such that modulus of G dashed of x less than or equal to k, where k is 2 by 3 and this is strictly less than 1. So, the second part conditions are also satisfied by G, and therefore, G has a unique fixed point in the interval minus 1 to 1. So, let us find out this unique fixed point. So, how do you compute that? A fixed point of this function is that p for which g of p is p. So, we must have p square minus 1 by 3 must be p. So, p square minus 3p minus 1 is 0. So, p is 3 plus or minus root of 9 plus 4 by 2. So, 3 plus or minus root 13 by 2. So, p is 3 plus root 13 by 2. So, its value will be bigger than 3, and the other one is 3 minus root 13 by 2, whose value will be less than 1. So, p equal to 3 minus root 13 by 2 is the unique fixed point for this function g in the interval minus 1 to 1. We note that g also has another fixed point 3 plus root 13 by 2, and this fixed point belongs to the interval 3 to 4, and we observe that g of 4 is 5 because g of x is x square minus 1 by 3, and g dash of 4 will be 8 by 3, and that is greater than 1. So, we observe that g does not satisfy the conditions of the theorem, because g does not take values within this interval, and in addition g dash of 4 is greater than 1, and therefore, g does not satisfy the conditions of the theorem that we have proved just now. Now, we know what is a fixed point for a function and what are the sufficient conditions for the existence and uniqueness of the fixed point for a function. So, now we would like to know how to find this fixed point for a given function numerically. The following result gives us a way by means of which we can generate a sequence of iterates which converge to the fixed point for a function g, provided g satisfies certain conditions. So, let us write down the statement of the theorem and see what the result says. We look at the result which is given by fixed point theorem. This states that if g is a continuous function in the closed interval a b and g takes values in that interval for every x in that interval, and in addition g dash of x exists in the open interval a b, and a positive constant k which exists with k less than 1, such that modulus of g dash of x is less than or equal to k for every x in the open interval a b. These are the same as the conditions that we have given in the sufficient conditions for existence and uniqueness of a fixed point for a function. So, if those conditions are satisfied, then the result says for any number p naught in this interval a b, you consider the sequence of iterates generated by p n equal to g of p n minus 1 for n greater than or equal to 1. What does that mean? You start with any p naught in that interval, so that when n is 1, you know p naught, compute g of p naught and call that as p1. When you know p1, find g of p1, that will give you p2, and so on. You generate the sequence of iterates starting with p naught in a b and using p n equal to g of p n minus 1. This sequence of iterates p n converges to the unique fixed point in the interval a b. So, if the conditions mentioned here are satisfied, then the sequence of iterates generated by Pn equal to g of Pn minus 1 starting from any P naught which lies in the interval AB will converge to the unique fixed point in the interval for the function g. So, this gives us a way to find a fixed point of the given function g numerically, correct to the desired degree of accuracy. So, let us see the proof of this result. So, by the conditions specified in the earlier theorem, which are sufficient conditions for existence and uniqueness, which are the same as given here, a unique fixed point for g exists in the interval AB. Now, g takes values in AB and g is a function from AB to AB. So, now I consider the sequence Pn which is generated using Pn equal to g of Pn minus 1. So, g takes values in that interval AB and therefore, all the Pn's which are members of this sequence, they are all defined for every n, for n greater than or equal to 0, and Pn belongs to AB because Pn is g of Pn minus 1 and g takes values in the interval AB. So, Pn belongs to AB and this is so for each n. And now use the fact that modulus of g dash of x is less than or equal to k. So, that for each value of n, let us find out the difference between Pn and P in absolute value. So, Pn is g of Pn minus 1, P is g of P. So, mod Pn minus P is mod g of Pn minus 1 minus g of P. So, by mean value theorem, there exists a psi n belonging to the open interval AB such that modulus of g of Pn minus 1 minus g of P is modulus of g dashed of psi n into mod Pn minus 1 minus P. But this is less than or equal to k. So, k times mod Pn minus 1 minus P. So, I now have shown that mod Pn minus P is less than or equal to k into mod Pn minus 1 minus P. So, I apply this result inductively. So, what do I know about Pn minus 1 minus P? That will be less than or equal to k times Pn minus 2 minus P in absolute value. So, this will be less than or equal to k square into mod Pn minus 2 minus P. So, again that will be less than or equal to k cubed into mod Pn minus 3 minus P, and continue this, and this will be less than or equal to k power n into mod P naught minus P. And what is P naught? P naught is any number in AB with which we have started our iterations. So, what have we shown? We have shown modulus of Pn minus P is less than or equal to k power n into mod P naught minus P. But what do we know about k? K is positive and it is strictly less than 1. So, limit as n tending to infinity of k power n will be 0. And so, I take limit as n tends to infinity on both sides of the result that we have shown. So, limit as n tending to infinity of mod Pn minus P is less than or equal to limit as n tending to infinity of k power n into mod P naught minus P. But this goes to 0. So, limit as n tending to infinity of mod Pn minus P is 0. What does that mean? It means that the sequence Pn converges to P. And what is this P? P is a unique fixed point for the function g which lies in the interval AB. How is it guaranteed? The conditions which are given here are nothing but the sufficient conditions for existence and uniqueness of a fixed point for the function g. So, Pn converges to P, and this P is the unique fixed point for the function g in the interval a b. So, the sequence of iterates generated by Pn equal to g of Pn minus 1 starting with P naught in the interval a b converges to a unique fixed point for the function g in the interval a b. And this theorem is called fixed point theorem, and it gives us a way of finding a fixed point for a given function which satisfies certain conditions by generating a sequence of iterates which converge to the unique fixed point for this function. This result also has the following corollary. So, let us look into the result of the corollary. The corollary says, if G satisfies the conditions given in the fixed point theorem, which we have proved just now, then the bounds for the error involved in using Pn to approximate the fixed point P are given as follows. Namely, the absolute error is less than or equal to k power n into maximum of P naught minus a comma b minus P naught, and the absolute error is less than or equal to k power n by 1 minus k into modulus of P1 minus P naught, and this is so for every n greater than or equal to 1. So, the corollary gives us a bound on the absolute error when we approximate by Pn the unique fixed point P for the function g. So, let us try to understand the proof of this result. We know that the fixed point P belongs to the interval a b. So, Pn minus P in absolute value is less than or equal to k power n into mod P naught minus P. This we had shown in fixed point theorem. So, I am making use of that result. So, mod Pn minus P is less than or equal to k power n into mod P naught minus P. So, that will be less than or equal to k power n into this will be maximum of P naught minus a comma b minus P naught. So, that gives us the first result. Now, let us consider the proof of the second result. So, let us start with mod P n plus 1 minus P n for n greater than or equal to 1. But P n plus 1 is g of P n and P n is g of P n minus 1. So, that will be less than or equal to, we have already seen all this. I can use at this stage mean value theorem. So, the absolute value of this will be less than or equal to g dashed of psi n into mod P n minus P n minus 1. Modulus of g dashed of psi n is less than or equal to k, and therefore, this will be less than or equal to k into mod P n minus P n minus 1. I apply this result inductively. So, that will be less than or equal to k square into P n minus 1 minus P n minus 2 and so on. So, it will be less than or equal to k power n into mod P 1 minus P naught. So, what have we shown? We have shown for n greater than or equal to 1, mod P n plus 1 minus P n is less than or equal to k power n times mod P 1 minus P naught. Now, I consider m greater than n greater than or equal to 1 and consider the absolute value of the difference between P m and P n. So, P m minus P n is P m. Now, I subtract P m minus 1, add P m minus 1. I subtract P m minus 2, add P m minus 2 and continue. I subtract p n plus 1 and add p n plus 1 and then write down this which is minus p n. So, whatever that I subtract I add, and therefore, I do not make any change in the left hand side, but I only rewrite this in this form. And now I apply triangle inequality. So, modulus of a plus b is less than or equal to mod a plus mod b, and extend this inequality and use that result here. So, this will be less than or equal to mod p m minus 1 plus mod p m minus 1 minus p m minus 2 etc. plus mod p n minus 1 minus p n. But we have just now shown mod p n plus 1 minus p n, namely the absolute value of the difference between successive iterates is less than or equal to k power n times mod p 1 minus p naught. So, we see that this is the absolute value of the difference between the mth and the m minus 1th iterate. So, it is less than or equal to k power m minus 1 into mod p 1 minus p naught. This is the absolute value of the difference between the successive iterates at m minus 1 and m minus 2 step. So, this is less than or equal to k power m minus 2 into mod p 1 minus p naught. And continuing this argument, we have mod p n plus 1 minus p n will be less than or equal to k power n into mod p 1 minus p naught. So, we have k power n into mod p 1 minus p naught. If I remove this as a common factor, then I have 1 from this. The previous term will give me k, the last but 2 term will give me k square and so on, and this term will give me k power m minus n minus 1. You just see k power n times k power m minus n minus 1 will be k power m minus 1 times mod p 1 minus p naught, which appears here. Now, by fixed point theorem, what do I know? The sequence of iterates p m generated using p m is equal to g of p m minus 1 converge to p. So, limit m tending to infinity of p m is p. Therefore, what is mod p minus p n? So, that is limit as m tending to infinity of p m, because the limit is p minus p n. So, this will be less than or equal to limit m tending to infinity of, right, we require what mod p m minus p n is, and that is what we have computed. What is it? Mod p m minus p n has been shown to be less than or equal to k power n into mod p 1 minus p naught into this. That is what I have written, k power n into mod p 1 minus p naught into this can be written as summation I is equal to 0 to m minus n minus 1 into summation I is equal to 0 to m minus n minus 1 of k power I. When I is 0, you get 1, when I is 1, it is k, and so on. When I is m minus n minus 1, you get k power m minus n minus 1. But this series has finite number of terms. So, the sum of this series is less than sum to infinity of the series sigma I is equal to 0 to infinity k power I. Now, what do you know about k power I? K is such that k is less than 1 and k is positive. So, sigma k power I is a geometric series with common ratio k such that 0 less than k less than 1, and therefore, I have sum to infinity of such a geometric series. So, the geometric series converges to 1 by 1 minus k. So, I substitute that value here, and so I end up with mod p n minus p less than or equal to k power n into mod p 1 minus p naught into sum to which this series converges to, which is 1 by 1 minus k. So, I have the result that mod p n minus p is less than or equal to k power n by 1 minus k into mod p 1 minus p naught, and that completes the proof of this part. So, these give you the error bound that is involved in taking p n as an approximation to the unique fixed point for the function g in the interval a b, where g satisfies certain conditions, namely the conditions listed in the fixed point theorem. So, what is it that we have done all along? We defined what is a fixed point for a given function g, and how do we determine this fixed point? Numerically, namely if g satisfies certain conditions in an interval a b, starting with any p naught in that interval, we can generate successive iterates using p n is equal to g of p n minus 1, and this sequence of iterates generated by p n is equal to g of p n minus 1 will converge to a unique fixed point for the function g, provided g satisfies the conditions in fixed point theorem. Then we wanted to determine the absolute error in taking p n as an approximation to this unique fixed point, and we have error bounds given in the results of this theorem. So, we now have completed our discussion about the fixed point problem. We know what is a fixed point, we know the sufficient conditions under which there is a unique fixed point for a given function, and we know how to compute this numerically, and we also have an error bound by taking p n as an approximation to p. So, the problem that remains is to connect this fixed point problem to that of root finding problem, and we shall do this in the next class.